Now we'll move on to chapter 6, which is just a continuation of chapter 5. Basically, you might as well put the two chapters into a single chapter. But anyway, this continuation. So, because now we have this vector space and define vector and operator in the vector space, and we can use that to solve for equation. And many equation has the form of in this vector space. We want to know the operator, the operator on the vector side is proportional to the side itself, just proportionality constant lambda side. And this operator, again, this can be any operator, like a differential operator, an integral operator, or something else. But whatever that is, this is satisfy this kind of equation. And the equation is to solve for this proportionality constant, which we call the eigenvalues, and also what the psi corresponding to the eigenvalue. Those are what we call the eigenvector. So this is the so-called eigenvalue problem. So basically solving two things for eigenvalue problem. Equation like that, you want to solve eigenvalues. So we can have a finite number of eigenvalues or infinite many eigenvalues. But for each eigenvalue, you can find an eigenvector up to a constant. Obviously, this is a linear equation. So you can multiply by any constant. It's still the same, satisfy the same equation. Right? And then and many physics problem is like that. If you go back to this ordinary physics equation, this can be a differential operator, like this would be a differential equation, and solve for an eigenvalue problem for a differential equation. That's the general format. But now, if you introduce a set of bases in this vector space, and you can now change that to a matrix problem. Say if psi is given by psi is given by sum over I, c sub I by I, right? And then A have the A matrix element, let's say A, you have the matrix element Ij, which defines this little Aij, and it's given by this by I, A, by J. So basically, you introduce a set of bases psi, and then express your vector and your operator in the basis. And that becomes this equation, you can transform it to a matrix equation. That becomes basically A, Ij, Cj, equals the lambda Cj. That becomes a matrix equation. Right? And so this is like a square matrix. This is like a column vector, and then equals to a constant times the same column vector. And the goal is to find what value of lambda, and then for each value of lambda, that what the Cj are to satisfy this equation. And we'll see that there's a process to solve it, and it depends on the dimension of A. So if it is a finite dimension, you have a finite number of eigenvalue lambda. So if you n by n matrix, then you have n values of eigenvector. If it's infinite dimension, obviously you have an infinite number of eigenvectors. Okay, and so that's the eigenvalue problem in matrix form. That's leading to second section. So the first section is very simple. It's just a very short introduction. The second section is just going back to this matrix, solving a matrix eigenvalue problem. So you can go back to even more elementary problem, and because of more advanced cases, you have infinite dimension. For infinite dimension matrix, whatever the presented in section 2 may not work. So, section 2 basically talk about this with a finite dimension, and you have a way to solve this finite dimension matrix eigenvalue problem. But when you extend it to infinite dimension, that there is, I mean, there can be method, but then it's more complicated than the method in section 2. So section 2 basically is a simplified example of this matrix eigenvalue problem. All right, maybe let's keep it like here first. So the first example in section 2 is just like a minimization problem or particle in a potential well problem. It's in classical problem. Like, so you have potential V that depends on coordinate x, y. Right. Now, basically, these are x, y. Now, going back to the geometrical problem, this is basically you already chosen a set of coordinate system or your basis vector, basis unit vector. Then you define your x and y coordinate like that. So this is already in a certain basis. They're given by this a x squared plus b plus b y plus cy squared. Right. So this is like potential, and then the force is minus squared phi is minus greater than v. Greater than v is your force. So it has the x component is obviously fx is this minus the gradient is minus 2ax minus by. Fy will be taking the y derivative is minus bx plus 2c1. Okay, so this is the force component, and eigenvalue problem is to try to find a direction in terms of xy such that f is proportionate x. You want f proportionate x. Because you want to find f is proportionate x such that you can basically reduce it to a one-dimension problem. If f is proportionate x, then the motion of the particle is stay within a straight line. You want to find, so you have an xy, original xy component, you want to find direction such that the force along this xy location is along this line, always along this line, because everything is linear. So it's just the angle is just only the angle is important. So with this angle, then the force is proportional to the x and y. So proportional to this position vector, so that the force vector proportional to position vector, so that the particle will move along this straight line. And there can be more than one direction. Obviously, you can have, in this case, another direction. So this is two-dimensional problem. So generally, there will be two directions that has this property. So what we try to find is f is lambda x. Right. That is what we, that eigenvalue problem. And then put it in a matrix form. So F is given by this one. So if you choose X to be a column vector, X and Y, right? And then this equation, this F, is using this form, and we put it in a matrix. So F is minus 2A minus B minus B. Oh, this also minus. There's no plus because everything is minus. Right? Minus 2C times Y. And that equals to lambda. Okay. So that's set up your matrix eigenvalue problem. Now it's in the matrix form. So all you want to do is solve for lambda that satisfies this equation. And for each lambda, you want to solve x and y up to a proportionality constant that for that particular lambda that satisfies this equation. Okay, so that's the idea. And is that okay up to here? Yeah. So the method is quite straightforward. Basically, you just combine the two, the left-hand side, right-hand side, to a single matrix, multiplied by x and y. And so this is implied. Minus 2a minus lambda minus b minus 2c minus lambda multiplied by xy. Yes, equals to 0. Right? And the equation for lambda obviously is the determinant of this matrix must be 0. Right? You learn about this in linear algebra, right? So a square matrix multiplied by a column vector, set it to 0, and for non-trivial column vector, then the determinant of that must be 0. Otherwise, you get only trivial solution that the vector is 0. Okay, so the equation for lambda is just absolute value, or the determinant. So the determinant of this matrix is just equals to, they multiply this and that, you have lambda square, right? And then you have 2a times lambda, 2c lambda, so plus 2a plus c lambda, this times this, right? This time this and this time that, and combine to this one. And now finally you have 2a times 2c, so you have 4ac. And then minus b squared. Right? And now this is a quadratic equation, you know how to solve that. So this will give you lambda 1 and 2, or lambda plus and minus. Right? Obviously, I don't need to write down, you know how to solve a quadratic equation that will give you lambda plus minus. Right? And then for each one, then you solve for x and y. And the reason I'm not writing it down, I think there will be explicit example with a specific A and B, other than writing the general formula. You can wait for that example. Right. I think that's it. Well, your text actually doesn't even write it there. But that doesn't matter. That doesn't matter. But generally, is you know how to. This is the equation for the eigenvalue. So I think there's a name, but this is called characteristic equation for the eigenvalue. This is the equation, and that will allow you to solve for the eigenvalue. But the way to solve for the eigenvector is simply once you get the lambda, you're going back to substitute each one, for each one, say lambda plus or lambda minus, each one you substitute into that, and then this equation will give you two equations, but the two equations are actually linearly dependent because the determinant is 0. And so that means that there's only one equation. You can solve for the ratio of x and y, so that satisfies this equation. This is a little abstract, but we go to this example 6.2.1 with specific values of a and b. That would make it a little easier rather than carrying all the a and b. I mean, you can do that, write down the general solution, but for specific a and b, so this is a and 1 is the 1, b is minus square root of 5, c is 3. It's kind of strange, but whatever that is. So that equation is changed to, or this equation. So minus 2a is minus 2, minus lambda, minus b is square root of 5, square root of 5, minus 2c is minus 6, minus 6, minus lambda. It gives us 0. Okay, not too bad. Right. And then the characteristic equation now is the same, lambda square and plus 2a plus c. A plus c is 4 times 4 times 8 lambda, and then plus 4ac. A times c is 3, 4 times a times c is 12. Right, 12, and then b squared is 5, right? 12 minus 5 is 7. Okay, and usually this is chosen so that the equation is easy to solve, so we can look for way to solve it by factorization. So I guess one is 7. The other is 1, right? So it is 7 lambda 8, 1 lambda 8 lambda, yeah. So there are two solutions. So lambda equals to 7 or 1, minus 7, yeah. Minus 7, minus 1. All right, so that's straightforward. Now, the eigenvalues are this. Eigenvectors just put it back, so you can do, I think your textbook going solve for -1 first, so it doesn't matter. So you're basically putting this back to here, so the equation becomes -1, -2, -1, plus 1 is -1, right? And 5, minus 6 plus 1 is -5. 1, 0. And you see that the two equations that you get is linearly dependent, so you only have one equation. So you can use either one of them. So minus x, so this implies minus x plus square root of 5y is 0. So x. So basically that give you the just the ratio of x and y. You can either just solve for the ratio and get an arbitrary constant out, or you can first just choose arbitrary value. Say if you choose x equals to, or choose y equals to 1, but maybe easier. If you choose y equals to 1, then obviously x is square root of 5. So xy is proportional to 1, and x will be square root of 5. Right? You're solving up to a constant, but sometimes you like to normalize it, so-called normalize eigenvector. So to normalize that, you can just divide it by the square root of the norm of the vector, right? So x squared plus y squared and square root. In this case, is 5 plus 1, 6, so square root of 6. So you can choose a normalization, so equals to divided by square root of 6. Right. That will make it normalized, meaning the vector have the length is 1, xy dot into xy is 1. Right? Then that's the first -1, and then the same thing is this. I guess we already used that, so that's fine. So, well, -7, so this is 7 minus 2 is 5. Then this is square root of 5, square root of 5. And 7 minus 6 is 1. 0. So again, it's linear dependent, so you can use any one of them. Maybe you use this, the second one may be easier. So it's 5x plus y is 0. Right? And again, you can choose y, like you choose y equals, you can, now it's easier to choose x equals to 1. X equals to 1, y is minus square root of 5. xy is equals to, so x is 1 minus square root of 5, and then again you can normalize that. Right? That will give you this, the second eigenvector. Did I get
1 by root 5, because if you take my y to the other side, it would become minus y. So,
right?
okay.
Y, I choose x is 1, so y is square root of 5, right? Minus square root of 5, right? And then the magnitude is 6. The magnitude is 6, so you divide it by the square root of that. Yeah. And so I guess I got, this is 6.6, right? The two eigenvectors, 1 minus 1, 6 minus 1, yeah. I mean, except that the sign, the textbook has a minus sign, it doesn't matter. So you're only solving up to a constant proportionality constant, so that involves -1. So you can multiply by -1 and get your textbook value. And okay, so that is there is x and y. And all right, so this is what we call so these two directions are what we call the principal axis. So you go back to this line. So you have the two lines. One is one is like x and y are proportional to this square root of 5 and 1, right? And this one is x and y is proportional to, now x is actually proportional to -1 square root of 5. And you see that for this example, they are orthogonal. The dot product between this direction and this direction is 0. And the reason we'll make clear in the next section, but the ultimate reason is that this matrix, the original matrix that we erased already. But the original the matrix is without this lambda is symmetric matrix, because this is 2 by 2, just this off-diagonal elements are the same. They are symmetric. For symmetric matrix, the 2 eigenvectors are orthogonal and perpendicular to each other. So we see that this generalized to what we call the Hermitian matrix later. But then you can, so this 2 direction called the principal axis, and you can also define your new coordinate system using this 2 eigenvector. Let's see, basically this, if you call this EX prime. So this will be your EX prime. Right. So originally you have the univector EX in this direction and EY in this direction, right? And this will be proportional to EY prime, right? And so this is, now you use the -1, this will be EY prime, right? So basically the this direction will be your new axis, and then you can define your x and y accordingly. Becomes x prime and y prime, and then express your original problem in x prime and y prime. I guess.
So if we get an equation like, even if it's a 3D equation, can we always put one of the values as 1?
Well, it may not. It may or may not be. It depends on the equation. Finally, so sometimes it's 0. Sometimes one of them. I mean, if one of them is 0, then for 2 dimensions, the other is automatically 1, right? Yeah, it's just a convenient way. It doesn't matter whatever you do is after you do a normalization, you get the same result upon the sign, so you can get a negative sign. Yeah, thinking about the transformation. This is okay. But this is not actually a transformation. This is like the original one that we. Yeah, this one. This one is just basically doing a complete square, and you'll get exactly the same. But I suppose you know how to do this. So if you define a transformation, change the x prime and y prime, it's just using this x prime and y prime, using a principal axis, this will be only involve square term of x prime and y prime. Basically now you want to do a complete square so that that's involving just square terms of x prime and y prime. Right, that is that can be done. I mean, you can figure it out, but the final equations using that, right? But we'll have exercise like that in the homework, but that's quite straightforward to do. But we can move on to a slightly more complicated problem. So this is now move on with this 3 by 3 matrix. So now this is like an abstract problem. So you have H, the matrix H is 0, 1, 1, 0. It's like 0. And the form, so that the form is simple, so that the characteristic equation would be simple. Make it easy to solve. So this multiplied by xyz around X, Y, Z, right? So the eigenvalue problem is like that. So the characteristic equation is just subtract lambda to this to the other side and take the determinant of the matrix is minus lambda 1, 0, 1 minus lambda 0, 0, 0, 1 minus lambda. And 3 by 3, usually he will get a third order equation. And I mean, it can be solved. You can look up the formula. Generally, you can look up the formula and solve it. But for this particular case, it's actually easier because this is just one element in the single, I mean, there's lots of zeros. So it's just this element multiplied by this determinant of this square 2 by 2 matrix. Right, so it's easy. 2 minus lambda multiplied by determinant is lambda square and minus 1. So that is 0. So there are 3 roots, so lambda equals to the first one is this term is 2. And for second term, lambda is 1 or minus 1. So there are 3 terms. Right. And 2, 1. Eigenvector, that will solve for 2 first. The 2 is, the matrix is minus 2, 1, 0, 1, minus 2, 0, 0, 0, 0. X minus Z equals 0. The solve an eigenvector is to solve this equation. And obviously, that can be solved easily if we just set x and y to 0 and z equals to 1, because nothing is multiplied by z. The whole third column is 0, right? So you can say x, y, z is 0, 0, 1. That already normalized, right? So okay, so the first one is straightforward. Just by inspection, you know that if you choose this 2, 0, you already satisfy the first 2 equations, right? And then the last one is arbitrary, and then you can choose it to be 1 so that it's normalized. So that is trivial. This is lambda equals to 2. Lambda, the next one, your textbook solve is 1. Lambda is 1 is minus 1, 1, 0, 1 minus 1 is 0, 0, 0, 1, 0. All right. Obviously, the first 2 rows will give you the same equation, right? Because not involving z, so it's x equals to y. X equals to y, and the last one is just z equals 0. So you can choose x, y, z is last one is 0. X equals to y, so 1 is 1, the other is minus 1, and then you divide it by the square root of length, right? That is okay. Well, x equals to y, x is 1, 1, yeah. X equals to y, not x or minus 1, 1. All right, so now it's minus 1. So 1, 1, 0, 1, 1, 0, 0, 0, 3. Right. Then again, z will be 0, and x is equals to minus y. So y is going to be like what I did last time. All right, that's kind of trivial. And okay, up to here, so all this quite straightforward, because there's a choice of the elements that make the characteristic equation single. All right, the next one Next example deal with the possibility. So you have a 3 by 3 matrix. You have 3 eigenvalues. So there's a possibility that 2 of them are the same, or all 3 are the same, even. But now we deal with this degeneracy problem. You have two eigenvectors correspond to the same eigenvalue. That's called degenerate. Right? So here's H. Now it's 0, 0, 1, 0, 1, 0, 1, 0, 0. Right. And the eigenvalue problem, the characteristic equation is minus lambda 0, 1, 0, 1 minus lambda 0, 1, 0, 1, 0. Now, that is actually not difficult. It's just a center element multiplied by the square matrix corresponding to the west. So it's minus lambda times lambda square minus 1. Right? That's the determinant. You can see so that 3 eigenvalues are 1 for this one, and then plus 1 and minus 1, that's a minus 1. Yeah. And then there's 2 eigenvalues are the same, so there's 1 and 1 are the same. Right? So you can solve for the eigenvalues, eigenvector corresponding to these eigenvalues. So solve for the non-degenerate one, so minus 1 first. So for minus 1, we have 1, 0, 1, 0, 2, 0, 1, 0, 1, 0. Increase it 0. Right? The first and the third will give you the same equation. The second one will give you y0, right? And the x and z, x plus z is 0, so x is equals negative z. So x, y, z is proportional to this 1 and minus 1 is 0. And the square root. Yeah. Right, so that is okay. Now that's for the degenerate eigenvalue, so you have 1. Lambda is 1, so it's minus 1, 0, 1, 0, and 1, 0. The whole thing, whole row is 0, 1, 0, 1, 0. And then x, y, z is 0. Right? And so the first and the third equation will give you x equals to y, x equals z, and y becomes arbitrary, right? The one, at least one, there are two solutions. The one is just simply it's just like this, except that both are the same sign. Right, that will solve this equation. But that is one solution. But there can be the second equation that is linearly independent of this one. So one possibility is just to choose arbitrary y, because y is multiplied by all zeros. Everything is 0, so that doesn't matter. And then you choose x and y both are 0, then we satisfy this equation. X, y, z. It's just 0, 1, 0. And in this case, if you choose it like that, the actual normal orthogonal to this one, or you're already orthogonal to this one. Sometimes you solve for this degenerate, the two degenerate eigenvector you solve is not normalized. But then because they are satisfied by the same eigenvalue, you can choose a linear combination of that and choose that as a new eigenvector such that the two eigenvectors are normalized. That you can use the so-called Gram-Schmidt method. The one subtract by the projection of the other one on the first one. We did that before, and choose two orthogonal eigenvector. Orthogonal eigenvector is useful in different cases, but then and we don't have to do it if it's not required. But if we require, then choosing orthogonal eigenvectors are straightforward between all these eigenvectors that have the same eigenvalue because they satisfy the same equation. So any linear combination of these vectors is still an eigenvector. So you can make it orthogonal. Is that okay? So that's called degeneracy. So that all these topics are quite straightforward. The exercise should be straightforward. Yes, they're restricted to 3x3 matrix. If you go to 4x4, then obviously it becomes much more complicated. And all these methods cannot be generalized to in a straightforward manner to an infinite dimension problem. I mean, sometimes for infinite dimension, and if the coefficient truncate fast enough, you can approximate it as a finite, but a large dimension matrix. But sometimes it cannot. But anyway, this is just like just an example how you, after you use a corresponding basis and change that to a matrix eigenvalue problem, and that's the general method to solve it. All right. So